Okay, so let's continue with the discussion of quantization of scalar fields. Let's just quickly recap where we are. Okay. What is that? Let's just quickly recap where we were. So basically, we have written down the Heisenberg picture scalar field, actually massive scalar field. Actually, I write it down. Linear scalar, massive scalar field. And basically it obeys wave operator plus m squared acting on phi is 0. And the solution looks like the following. So basically, the scalar field can be expanded in terms of its mode functions, right? So these guys, the exponentials, in fact, are the ones that solve this massive scalar wave equation, and it's the A's that are operators. So A and A dagger are operators, because we're quantizing the scalar field. And I should say E is the positive energy. Right? It's the square root of k squared plus m squared, which you can recognize as just the energy, the zeroth component of momentum, so to speak. So if you define k mu to be the positive energy, then it is basically given by E, K, and then K vector. If you want to think about a classical dispersion relation, classical but relativistic energy. And it turns out that if you want to, so again, to recap what we've been doing so far, so to obey the canonical commutation relations. So xp is I, and xx and pp are 0. So in the field theory language, this turns out to be phi of t commutated with pi of t. But at x prime, this needs to be I times delta function, x minus x prime. So to satisfy, in other words, to obey this guy, and as well as the xx guys are basically x of t phi of x and phi of x prime, but both at t. And the PP guy is pi of t of x and pi of t of x prime. Again, the momenta, the field momenta, and the field position, so to speak, at different times, at different positions, but same time, are all commuting variables. But it's really the phi and pi at different positions, but same time that gives you the delta function. And to obey this, it turns out that if you plug this in to these commutation relations, and as we said before yesterday, you can write down the postulate for what you want to be for the commutation relations for A and with itself, A dagger with itself, A with A dagger, in such a way that, for example, to get the delta function in space, you need to have a single momentum integral involving a plane wave to give you this delta function. But you can play around with it basically, and you'll realize that to simultaneously satisfy all three of them, this guy, and this guy, the solution is the following. You need the AK commutator with AK prime dagger needs to give you 2 pi to the d times delta function of k minus k prime. In other words, A and A dagger commutes except when their momentum are equal. And
plus and minus,
this one?
Yeah.
Oh, thank you. Yes. Minus, plus, and then minus. Thank you. Yeah, they better be the Hermitian conjugate of each other, right? Because we're dealing with a real scalar field, which upon quantization, we want it to be Hermitian. Yes, thank you. And then this will be AK prime, better commute, and therefore the Hermitian conjugate also better commute. Yeah. So, and these guys in particular should remind you of the simple harmonic oscillator algebra. Okay. So, in fact, that's what we're going to do. So we're going to, in fact, verify directly that this is not just a fluke. In fact, it is directly related to the simple harmonic oscillator algebra. And this is important. So let's, in fact, press ahead and see how that's going to work out. Again, the key point is to recognize that this holds for each mode, each momentum mode, right? So the complication here is there are infinite momentum modes. And so we have to integrate over all momenta. But otherwise, if you focus on the each k, and if you're familiar with the quantum mechanical simple harmonic oscillator, then the rest should go through. Right? So I will, at some point, at various points, I will remind you of what the analog is in the harmonic oscillator case. So in the quantum mechanical simple harmonic oscillator, 1G simple harmonic oscillator, you would have encountered that A dagger is in fact just 1. Okay, that's something that, and then you also have A is 1, is 0, and so is A dagger. This is clear because things commute with themselves. Usually, we will soon again discover a violation of this, but usually, things commute with themselves, right? So AA commutator is 0, and therefore A dagger should commute with itself. So what's not trivial in the quantum mechanical simple harmonic oscillator case is that A and A dagger do not commute. So think about that as holding for a single momentum mode. And so what's happening, what the replacement for this is that it becomes a delta function, right? Because it's a continuum. So it's not 1 anymore, but a delta function. So yes, so now we're going to go ahead and in fact work out the Hamiltonian of this field theory, and we're going to see how that in fact further corroborates the interpretation that these guys are really the raising and lowering operators for the simple harmonic oscillator. Field theory, in fact, the non-interacting massive scalar is in fact nothing but a bunch of harmonic oscillators. That's the goal. So let me just write it down. So claim non-interacting massive scalar is in fact an infinite collection of simple harmonic oscillators. Okay. So let's in fact work this out. So remember that, well, actually, let me write it this way. So remember that I can always decompose my scalar field into so this is T of X, and so I can write this down over momenta tilde of T K e to the I K dot X. Okay, and what's going to happen is that likewise for pi T of X, I can do the same, K and then pi tilde T K. And because these guys are Hermitian, you can check both pi and T are Hermitian. So phi tilde dagger of TK is in fact phi tilde of T minus K. Okay. And likewise for pi as well, pi tilde dagger is in fact pi tilde of T minus K. And why is this relevant? Because now we're going to start to write the Hamiltonian. What's the Hamiltonian? Hamiltonian is the total sum over all the Hamiltonian over every position. Right? So field theory is complicated because you have a degree of freedom at every point in space and in time. But if you want the Hamiltonian at a given time, that means that you have to sum over the Hamiltonian density at the same time, but at every position. Okay. What is this guy? We worked this out before. Hamiltonian density, remember, is just, well, sometimes I'm just going to shorthand my integration as x prime, okay, because sometimes it's just too much to write. And H in particular remember, is actually just 1/2 pi of tx prime plus 1/2 of grad phi tx prime squared, squared meaning dotted with itself, and then plus m squared over 2 phi of tx prime squared. Okay, and if you know your Fourier transform, what you will discover is that you can go from, I'm sorry, this is squared 2. So kinetic energy plus the kind of shear energy, right? Energy from gradient plus potential energy. In this case, potential is just a mass term. It's a parabola. The potential is a parabola. And so what I'm saying here is that if you know your Fourier transform very well, all these guys are quadratic. And if you have permission objects or real objects, you will discover that the integration of a of x prime b of x prime, when you go to Fourier space, it just goes to dk to pi d. And then what happens is that you simply replace a with a tilde of k and b tilde of minus k. Okay, so this is just a fact that I have to write down, and you can derive for yourself. Just insert your Fourier transforms, then what you realize is that you will have these plane waves that you integrate over with respect to x, and that will give you a delta function in k. And that's what will give you k and minus k here. So in this case, it will just, because of this fact, you will discover that this is an integral over k, including the 2 pi's here. This is what I mean by this k, and you will have 1/2, and pi will become pi tilde of t comma k whole thing squared, absolute value squared. If you're talking about real guy, but actually what I really mean, what I really should say here is the operator at k times the adjoint. This is what I mean. And then here the gradient will become basically k squared. But there's also m squared here. So in fact, it becomes a k squared plus m squared here, which becomes a energy squared. And then it's phi tilde of tk absolute value squared. Again, what I really mean here is, because they are operators, what I really should mean is that this is phi tilde operator at k times as adjoint. But it does work out. So I'm not going to be shy about just using this notation. And now we're going to work out what is it. What is it in terms of phi tilde and because I'm filming, so I can't use the other spot. It's going to look too small. Otherwise, I really shouldn't have erased my Fourier decomposition. But let me just remind you of what it is. Right? So phi is an integral over k, 1 over square root of 2e k, and then you have a dagger, a, and e to the minus I k dot x, where this k dot x is e, the k0 term is e, and in other words, it's unshadowed, right? It's not, k0 is not unconstrained, plus a k dagger, e to the I k dot x. Now I want to extract the Fourier. Extract the Fourier coefficient in meaning phi tilde. So what I want to do is I want to remind myself that this is e to the minus I k e to the I e k t, and then it's a plus I k dot x. And so this guy is the adjoint, the complex conjugate of it. And so this guy will contain a minus k dot x, but I can do a change of variables. So it will look like this. AK e to the minus I e t e k t, and then plus AK A for this term. If I factor out e to the I k t, that means I have changed the variables from on the second term from k to minus k. So this becomes a minus k vector dagger e to the plus I k t. So remember that the energy is quadratic in k. So it doesn't matter if I change k to minus k, it doesn't matter. But now I can factor it out and say it's I k dot x. Okay? So again, this used to be minus IKT, IKX. It used to be a minus IKX. But I've swapped the minus k for plus k. So I need to now replace k for minus k. But this remains unchanged. Right? So this guy is my phi tilde. So I can use this guy to do my calculation. That's all I'm trying to do. I'm trying to plug it in here to do this calculation. Remember, what is pi? Pi is actually just phi dot. So we can actually go ahead and do the calculation over there as well. Right. So what is pi? Pi is just going to be k1 over square root of 2ek. But remember, when I take a derivative, it's going to give me ek. And then I will have a, let me factor out the I. Actually, it's okay, let me put in the I. So there will be a minus I ak vector e to the minus I k t, and then plus I a dagger k vector minus k vector e to the I e k t e to the I k vector x. So I'm skipping one step, but basically it's just I just take the derivative with respect to time, because I remember that pi is actually just phi dot. Okay. And in fact, let me simplify this just slightly, because this is actually just nothing but square root of ek over 2. At this point, it should look very similar to the simple harmonic oscillator. If you have some experience there, you would notice that, for example, Q of x. So in the simple harmonic oscillator case, 1D quantum mechanics, you will discover that x is something like 1 over square root 2 omega, and then it will be, in the Schrodinger picture, you will have no time dependence, but if you do it in the Heisenberg picture, it will look something like a e to the minus I omega t plus a dagger e to the plus I omega t. Okay. So again, there's a slight complication from the fact that there's now a momentum dependence, but if you look back at your notes, in quantum mechanics, this should look familiar. Okay, so there's already here there's an analogy, and then likewise P in the quantum mechanics case is square root of omega over 2, and then you will have something like A. So after a phase factor, right? There's something like A e to the minus I omega t, and then minus let's see. Plus A dagger e to the I omega t. Something of this sort. Yes. Yeah, so you'll find something like that in your quantum mechanics discussion of the harmonic oscillator. And so let's press on, right? So why am I doing this? Because I'm going to plug it into this formula. So let's go ahead and figure this out. K. Oops, let me write that properly. So h of t is an integral over k, and right, and so we have the following. We have 1/2, and then we have basically pi, which is this guy multiplied by itself, so ek over 2, and then let's multiply minus ik e to the minus ik t plus I a minus k dagger e to the I k t multiplied by the same thing, but with k swapped with minus k. Right? That's basically, or just a complex, just a dagger of this guy. So let's go ahead and do this. So it was plus I a k dagger, and then it's e to the I k e k t, and then minus I a minus k, and then e to the minus I k e k t. Okay, and then we got to plug in the ek phi tilde, ek squared from here times phi tilde squared, which is 1 over 2, okay, from that, and then we do ak e to the minus ik e to k t plus a minus k dagger e to the plus ik e k t, and then multiplied by this adjoint ak dagger e to the I k e k t plus a k minus a minus k e to the minus I e k t. Okay. And so you see that we have ek in the there's a common ek. So let's in fact pull it out. So integral over k, you have ek over 4 for now, right? Yeah, 4. and then so right, and so now we can plug that in. Okay, so we can now plug that in. So this is minus, and then minus EQ times AQ dagger, and you get plus EQ AQ dagger. Okay, and so after the break, we will see how does this lead to a particle interpretation of at least for these non-interacting massive scalars. I should say, you might complain, oh well, they don't interact, so why should I care? So as I said before, most of what we know about quantum field theory, the testable results that come out of particle physics, in fact, comes from perturbation theory, right? So the one exception is the strong force, but there, is a very difficult topic because you have to discretize it, put it on a computer. There's no simple description of, for example, the mass of the proton. Right? How do you calculate the mass of the proton? You have to put it on the computer and spend, from what I hear, months, running on the computer. So probably there's much to understand there in terms of human understanding. Right? The computer understands it, not us. But the rest of the standard model of particle physics is known through perturbation theory. So this is basically the groundwork. And once we introduce interactions, this interpretation will still hold, right? Because the interactions are weak. And so what we're going to say is that our particles are basically these, what we're going to introduce after the break. And then the interactions mainly mean that these particles will talk to each other, will scatter off each other, will annihilate each other, and so forth. Don't downplay the importance of what we're doing here, even though it is non-interacting, right? And if you think about it, who cares about non-interacting particles? You can't even detect them because they don't interact. But because they form the groundwork, it is important to understand these concepts well, so that you get a good intuition for what's going on when you do turn on the interactions. Okay, so let's take a 10-minute break, and we'll resume. I think it's 11 on my clock, so resume at 11:10. Okay, so what we're going to do is we're going to use these raising operators in particular to create what we'll call the one particle, two particle, and so on states. So let's report what we found. Right? So we discovered that the commutator of H with AQ is minus EQ times AQ. And then we found that the commutator of H with A dagger Q is plus EQ A dagger Q. So let's say we have found an eigenstate of the Hamiltonian. Okay, actually, better to talk about the regularized one because then you complain that all the energies are infinite, and there's nothing to talk about because everything is infinite. Well, what is there to talk about? So let's talk about H prime. Okay, so remember this is the regularized guy. And let's suppose that we found an energy eigenstate. Okay, so this is E script E times E ket, meaning it's an energy eigenket, energy eigenstate. And now let's ask ourselves, how do you get from one eigenstate to the other? And this part should be familiar from again from the harmonic oscillator discussion in quantum mechanics, but we should at least see it once. So for example, I can now apply AQ on this energy eigenstate, and I can ask, what is this? And I claim this is an energy eigenstate as well. So if I give you one, I can generate others. So let's see how that works. So I'm going to apply H prime to this guy, and again I'm going to use this trick that I can work out the commutator. I can write it as a commutator of H prime with AQ. Okay, there's H AQ minus AQ H prime. So I better subtract out the AQ H prime term acting on the energy eigenket. And this is where we use the commutation relations. So what that gives me is that I will now have minus EQ and then AQ. And remember, this guy acting on the energy eigenket is nothing but the original energy script E times AQ, all acting on the original energy eigenket. So A acting on E, now we can collect, is indeed an energy eigenstate as well, but now the eigenvalue is different. Yeah, so this is an eigenket. Why? Because I acted the Hamiltonian on this state, whatever the state means, and it spit out for me an energy eigenvalue, except it's not script E anymore, but actually is now energy lowered by minus EQ. So energy is now E minus capital EQ. So whatever it was is now being lowered by exactly one unit of energy consistent with basically one particle, right? This is minus one particle, so to speak. And if we do the same thing for A dagger, then we'll discover that will raise the energy by exactly one particle with momentum q. So let me just say that so lowers the energy by one particles with momentum q, because that's exactly what this is, right? Capital EQ is the energy of one particle with momentum q. And then let's now do this the similar calculation, but for A dagger. Right? So again, this state I claim is an energy eigenstate. How do I check? I now apply my regularized Hamiltonian to it, and again, use the same trick. I commute H prime with A dagger, and then I better subtract it out because it's H A dagger, not commutator. So in particular, I need to subtract out the term where I have A Q dagger H prime, and all acting on E. Okay. And what is this? This is in fact where I use this computation relation and gives me plus EQ times AQ dagger plus, now each time acting on E by assumption was my script E times AQ dagger, all acting on E. Okay. And so again, I can factor out my new energy eigenvalue is script E plus capital EQ, and then it's AQ dagger acting on the original cat. So again, I applied my H, I applied my H prime on my cat, and I get back my cat, but now multiplied by an eigenvalue, which is one unit of E of momentum Q, increased relative from script E. Okay. So now the energy, so let me write it here, energy, energy is E plus EQ, and this is basically increased E by one particle with momentum Q. Okay. Now, we notice that with the, let's now notice something which is also a crucial part of the argument, that H prime must have a minimum eigenvalue. Okay, why do you do this? Well, let's take the expectation value of H prime. So H prime, remember, is, let's write it out, integral over K, EK, and then AK dagger, EAK. Psi, that's the first part. And then there's a part that is, which I call the zero energy, right? And so that would just be zero energy times psi. Psi is completely arbitrary at this point. I just want to show you that whatever this is, there's a lower bound to it. Okay, and so what do we have here? We have the following. We have AK acting on psi dagger, and then integral over K, EK, AK psi, okay, plus E naught. I'm assuming that psi is 1. If it's a physical state, it better be normalized to 1. So what we have here, this I can call psi prime. So we have psi prime integral over K, EK, psi prime. In fact, I can now pull it out, right? So I have now psi prime, EK, plus E0. Okay. I should say, of course, these guys depend on K. But the point here is that all of these guys are positive. Okay. And whatever this bound is, so this must be, provided this converges, must be greater or equal to E naught. Okay. So there must be a lower bound. Again, upon regularization, this is always a tricky problem in quantum field theory, right? So if I had made this argument with the unregularized guy, then people who care about rigor will tell me, hey, you have the infinity, so you can make infinity anything, right? And then my argument breaks down. So there's some ambiguity there, right? If you care about complete rigor. But we're physicists, right? So if you buy my argument, we can regulate it, and with the regularized Hamiltonian, then I claim it must have a lower bound. And this is important because that means that there must be a point where I can keep lowering. So remember, I can lower the energy by 1 unit, and by just applying the lowering operator. I can also raise it But raising, seems to me that you can keep going, right? You can keep increasing energy, by the way, but this is actually one place where gravity will probably play a role eventually. If you pump too much energy into one small volume, eventually you will form a black hole. So this is one place where gravity will play a role, but we won't go there. But the lower bound, if you buy my argument here, there must be a lower bound. That means I can keep lowering my energy, right? I take whatever state I start with and I keep lowering. At some point, it must hit the zero vector. Because if there's no zero vector, when I keep lowering, then there's no bound. There's no lower bound. Okay? So let me just write it down to make it clear. There must be, and that in fact is our ground state. Exactly the same argument is made when you do the one-dimensional simple harmonic oscillator. But I want to say it here just to make it clear. So we can keep lowering the energy right? So if you take your original energy eigenstate epsilon and you keep applying AQ1, AQ2, AQN, this state has energy what? You have energy epsilon and then you lower it by EQ1, lower it by EQ2, lower it by EQ3, and so on. You can keep going. So, but each prime has a minimum energy eigenvalue. Right? So therefore, there must be a point where there must be a ground state, which I'm going to just write it as 0. There must be a ground state such that any lowering operator acting on it gives you 0, the 0 vector. Okay. Because otherwise, again, if it doesn't happen, so proof by contradiction, right? If it doesn't happen, that means you can keep going. You can keep lowering the energy eigenvalue. And then there's no minimum. But that's a contradiction, right? We just proved, we argued that there's no lower bound. There is a lower bound, right? We just argued that there is a minimum eigenvalue. So therefore, this must happen. And this is in fact the ground state. So 0 is the ground state. It should also be said that again we're doing non-interacting QFT. So in this case we can solve it exactly. So we did this. We've now done this in the basis where the Hamiltonian is diagonal. Right? We've diagonalized the Hamiltonian by writing it as a sum over the momentum modes involving raising and lowering operators. And we're going to pursue it further until the end of this class. But it should be said that you can also go to the Schrodinger picture. Right? So far we've been working, because of relativistic invariance, we've been working mainly using the Heisenberg picture. This is advantageous because you solve wave equations, we know what the mode solutions are, and so on. But we'll probably by next week, we'll actually also see how you can use the same formalism to get the Schrodinger picture vacuum wave functional, right? The analog of the Gaussian. So if you remember, in the harmonic oscillator case, in quantum mechanics, the ground state wave function is a Gaussian. So we will discover, I think you will discover in your homework, but I'll tell you a bit about it, that the analog of the ground state in quantum field theory is a wave function though. So you give me you give me a field, and I tell you what's the probability that the field will actually be found in that configuration. So it's a very intricate object. It's no longer the question of I give you a particle and I ask what is the probability the particle is found in some position. It's now a field because we're doing field theory, and I ask what's the probability that the field is found in some particular configuration. So this takes a little bit getting used to, but at least we'll solve the vacuum wave functional for the non-interacting massive scalar field. And why am I talking about this? Because people sometimes will say this, right? So when we do classical mechanics, we can one body problem is easy to solve, right? Just constant acceleration because there are no external forces. Two body problem, okay, you're going to struggle a little bit with it, right? So 1/r potential. It's tough, but by the time you reach maybe third year of your undergrad, you can solve it with some effort, of course, right? You have to know some conservation laws, energy conservation, angular momentum conservation, and actually there's an additional Runge-Lens vector that's conserved, and then you can solve the Newtonian gravity or the Coulomb potential problem for the two-body problem. The problem is that when you come to quantum field theory, you can solve the ground state for the non-interacting case, but once you turn on interactions, it becomes so difficult that, like I said before, for example, for the strong force, you're going to put it on the computer to even solve for something as simple as what's the ground state, right? And so, it's not known, right? We don't, for example, you can ask what's the ground state of the standard model. We don't have an exact answer to that. But you can calculate Feynman diagram of the Feynman diagram. So the zero body problem in interacting quantum field theories is very tough. Okay, and for example, in the strong force case, you can win $1 million for in fact rigorously by mathematician standards, where you can rigorously define what Yang-Mills theory is. We won't go there. I don't think we'll have the time to do that. But basically, you have to do what is called non-abelian gauge theory, and even that it's not clear, at least to the mathematicians. I think the physicists will have arguments to show that there's some area law. Anyway, it's a whole body of knowledge that unfortunately we won't have the time to go into. But you should take, if you want to be a theorist, you should take second semester of QFT, third semester, fourth semester. If you do until you become a professor, you should still be studying QFT. QFT is a very deep, very broad subject, right? And so papers are still written about it, and so that's why, because it's a tough problem. And that's how tough it is. Even the zero body problem is tough. Anyway, so that's an aside. But now we should make a slight detour, like I said, and want to, in fact, define the n particle states. But I want to define it in a relativistic case. And so let's, in fact, see how we do it. So this is the ground state. And so I claim that the one particle state needs to be defined in a particular way. So I will need to introduce a factor of 2 times the energy square root, and then multiply it by the raising operator. So this, in fact, is the one particle state with momentum Q. Okay, that's this guy here. And by the way, we're doing a real scalar, so there's no the particles and the antiparticles are the same, right? So that's why I don't have to worry about it at this level. But later on, when we do the direct equation, then I think I'll have to try to elaborate on that point a little bit more. So if you are wondering about it, don't worry about it for the moment. Because the particles, these are the particles, and there's no basically there are also the antiparticles, but we'll go there in a little bit. So this I will simply define as Q. Okay, so when there's only one particle, there's one Q, there's no ambiguity. And then, but of course, I can go on and define, say, the n particle case. And now I need to introduce n momenta. So n particle state with Q1 to Qn will therefore be square root 2e Q1 times square root 2e Q2 all the way to square root 2e Qn. And then I will have my raising operators Q1 dagger, AQ1 dagger, all the way to AQN dagger, acting on the ground state. This is my n particle state, which I will denote as Q1, Q2, all the way to Qn. And even at this point, there are a few things to say. The first thing to say is that this is the slight departure from the quantum mechanical harmonic oscillator. In the quantum mechanical case, I think you can get away with just saying a dagger on the ground state is your excited state. Oh, I'm sorry, I forgot. I almost forgot. I always forget when I teach this. There's a 1 over square root of n factorial here. That's important. And the reason for this factor of square root 2e is in fact relativity. So why is that so? So in fact, let me change. So let me say the square root 2e is important for relativistic invariance. And so I think in fact Pascal and Schroeder complains that sometimes some books don't normalize it in this way. So I don't think it's quite right. So what do I mean by this? So in fact, let's consider the normalization, right? So k prime, what happens here? So this is in fact, remember, square root 2e, k, acting on, and then ak dagger, acting on the ground state, dagger, right? So this is k. And then it acts on the bra. This bra is now acting on square root 2e k prime, and then ak prime dagger acting on the ground state. Okay. Stuff. And so now, what do you get? You get ground state, and then square root 2ek, square root 2ek prime, And then you have AK, because you take a dagger of the dagger, becomes AK, and then AK prime dagger, all acting on the ground state. But this guy here, we can manipulate it again using the commutation relations. We're going to say that this is AK commuted with AK prime dagger plus, again I need to cancel out AK prime dagger, AK. Okay. And then remember that for finite momentum, AK acting on 0 is a 0 vector, which means you can throw it away. Okay, so that's the crucial point here. When you commute through, AK acting on this is 0. So in fact, this can be thrown out